questions, just drop either stop me, speak up, or you can put it in the chat box. Don't wait until the very end. It's always good to have a discussion while we are speaking, while we are talking. And if you put questions in the chat box, either I will have a look at this, or maybe Professor Sarangi can see if there are any questions. Uh, right. So I work at University of Glasgow in the School of Engineering, and also I'm part of this Glasgow Computational Engineering Center, where we do a lot of work on computational mechanics, computational physics. And I'm going to speak about magneto-mechanical coupling. So specifically soft materials, uh, elastomer types of materials, which can be influenced by external magnetic field. And it's nonlinear because you are typically working with very large deformation or large magnetic field, and the effects are nonlinear. And we'll talk a bit about how these materials are used, and how do we model them. So my group essentially has been working on mathematical models and computational models for this type of problems for many years. Uh, and I would like to just show you some overview of what we have done. I'll try to not go into too many details, too many mathematical details, because I understand it's just after lunch and we don't want to do too much maths right now. But I'll still present a little bit of mathematics just to make sure that things are at least the essentials are conveyed. So before I begin, I just want to kind of speak a little bit about University of Glasgow. This is one of the pictures of our lovely campus. And the reason I want to talk about this is because I would love as many of people around here, either it is whether you are a student or whether you are a faculty member. We have a lot of visiting programs. We have educational programs. So I would love if you can come and visit. This is one of the oldest universities in the English-speaking world. It was founded in 1451, so many centuries ago. And we have a very nice history of mechanics. Uh, so I'm part of this Glasgow Computational Engineering Center, where we do a lot of you know computational physics, uh, all sorts of finite element method, all sorts of mathematical approaches. There is also soft mech center, which essentially deals with soft materials with a focus on biological tissues like heart, arteries, and so on. And there are many other centers which essentially focus on different aspect of mechanics, different aspect of computing, and we work on a lot of modern problems. And I have been quite lucky in the sense that I have because we are fortunate to be in a nice environment. We get a frequent visitors. In fact, I think a couple of people in the audience have been here. I get many visitors from IITs, both faculty members and students in different capacities. And we just love to work with people. We believe in collaborative work because collaboration can kind of lead to nice results. We have very nice open source projects. I don't want to talk too much about them, but if you are aware of open source projects, then you know that they are quite useful to be part of. So yes, this slide is just here to say that you're welcome to visit. You can kind of contact people within the centers within the university, and there are many mechanisms through which we work with people together. Right. So that's about a little bit aside. So coming back to the topic of today's conference, uh, and this is a slide I like to show because I grew up in 80s and 90s, and when we were growing up, these were the movies that kind of predicted how the robots are going to be in the future. They and and I hope people know some of these movies, Star Wars and Terminator and Wall E. And if not, maybe you can go and watch them over the weekend. They're quite nice. But the essential idea was they were all focused on robots from the future or in the future, And all those robots had these clunky metallic parts, as you can see on the screen. And they could do amazing things, but they were essentially rigid bodied. uh, and this was there because people in 70s and 80s and 90s didn't have a lot of experience working with soft materials. At that time, I think steel, metal, they were the, let's say, cutting edge materials at that time. And what we have realized since last few decades is that if we continue working with these rigid materials, these metallic materials, which are very heavy, which are very difficult to manufacture, which are also expensive, uh, uh, I think they impose a lot of restrictions on what we can do. Uh, this is what the really amazing machines in nature look like. You know? So on the left is an octopus. On the right is the heart uh, inside every one of us. And if you look at them carefully, the amount of different things that these machines do is just outstanding and amazing. First of all, they're all flexible, soft materials. Let's focus on octopus for a second. Uh, so everything, there are hardly any bones there. I don't think there is any bone at all. Maybe very few. It's all soft material. It can squeeze through very tiny spaces. It's intelligent. So there is a computing unit. There is a brain inside there, which works quite well. Uh, all these tentacles, they have got multi functions. So they've got these. They can grip things. They can move around. They can work very flexibly. They're also very lightweight because of soft materials, but they're very tough. So it's not easy to break them. Uh, right? They are because they're biological tissues. They've got a self-repairing nature. So if there is a cut, if there is a tear, then there is a way to repair it on its through the biological mechanisms. No? There is octopus can change color. So there are certain things on the skin, on the surface, or in fact through the entire tissue that can kind of cause changes in the color. There is multi-physics coupling there. There are all these neurons that carry electric field. There is obviously flexible mechanics going on. So I think when you look at these machines, which are extremely complex, they have evolved over millions of years, and they are in a very amazing state. I think this is what the future of robotics is. And when you see the recent advances in robotics, people have been trying to mimic machines like Octopus or the Heart or these soft machines because of all these advantages. They are very cheap in the sense that manufacturing using something like an elastomer is very cost effective compared to manufacturing something like steel or iron. So I think these are one of the reasons why people in engineering have been moving into this space, and they want to explore more in this space. And it's a very open problem. If you are a PhD or a master's student or an early career academic, and you are thinking about problems that you can work on for the next few decades, I think soft material mechanics is one of the nice problems. And then you have coupling with electric field, magnetic field, other kind of physics, which make it quite interesting. Uh, so here I would just want to show you a couple of videos from a very recent paper. The reference is right here. And because my talk is about magneto-mechanical coupling, I'm just going to focus on some recent advances that have been made in coupling of mechanics with magnetic field. So this is kind of a robotic. Okay, let me see how I can play it. Yeah. So on the top left, you see a small robot. Uh, I should have reduced the sound. Okay. You can see a robot that is moving along in a very tight environment and which is trying to mimic inside of your body. So this environment is trying to mimic, let's say, some intestine or some blood vessel inside the body, and you can see some magnetic field is being applied, and that magnetic field is like a pilot. The pilot sitting outside, and that tries to move this very small robot through this very narrow, tight space. Uh, and a very important thing about this robot is that there are no wires attached to it, right? So if you want to send something inside the body, you don't want wires attached to it or cables attached to it. Magnetic field can be applied remotely, and I think that's why these kind of robots are very uh, popular, in the sense people have been working on it so that they can make them smaller and then actually use it for biomedical applications. On the bottom right is another movie like that shows targeted drug delivery, right? So this is again a robot similar to the one on the top. It moves in a certain location through again by application of magnetic field, and then the temperature changes, and this changes in the temperature, it will cause, as you can see, the temperature here, and then you see a capsule here. This capsule can be obviously opened up because of changes in the temperature, and then you can release whatever medicine you want to release, uh, and then the robot goes away, right? So this is something which is very interesting, which we call as targeted drug delivery. And this is again a biomedical application where instead of asking a patient to, take a capsule and then it goes everywhere in the bloodstream, the medicine goes everywhere in the bloodstream, and then you hope that some of that medicine reaches the place where it's supposed to reach. You can actually very precisely move around and put the medicine right at where you want it to be. Uh, so this is just to set the scene that why these robots are important, and the kind of things that they can do. And there are many more examples. You can see some of the recent papers which will tell you how people have been using them. And these are all because the inside of our body are all soft tissues, blood vessels, intestine. These are all soft tissues. So you want something that is soft to interact with them. If you put something which is like this, like rigid body or a steel, there is a possibility it can cause tears and scratches inside of your soft tissues. And if it is something which is soft itself, like a rubber or elastomer, then this possibility of injuring the tissue inside is quite less. So this human body and robotic interaction requires soft materials, uh, and in order to make those soft materials work, you need external fields like magnetic field in this case, temperature again in this case, or electric field, or other kind of physical coupling. Right. So this is moving forward. I want to focus on magnetorheological elastomers, and these are the kind of materials which I've modeled over the few years, and I would just like to show you some ideas around it. So what are these materials? This is just an SEM image, and essentially it's all about particles which can be okay. Let me change the pointer again. Particles which can be ferromagnetic, which means like iron, or which can be permanent magnets. And these are distributed inside the material. So if you distribute them like this, you get an isotropic material. If you distribute it along a certain direction, you get an anisotropic material. They have their own advantages. But these are two different types of MREs that we have. One is called soft MRE, which is if the particles are iron particles or ferromagnetic. And another is called hard MRE, which is when you've got permanent magnets instead of that. Right? So, and these have different properties. But the essential idea is that when you put these particles inside rubber material or elastomer material, then you can create the robots like the one that I showed in the previous slide, because then it becomes magnetoactive. You can apply a magnetic field, you can change its shape, you can cause it to move around, you can cause deformation and so on. Right? So the idea is we've got these materials, and this is like a very simple way, very simple schematic. I mean, the reality is a little bit more complex, but this is how we do it. Like we Whenever you manufacture any elastomer material, you start with liquid elastomer. You mix with some matrix materials. You mix in some additives. You mix in some particles, uh, uh, and essentially you try to mix it efficiently using some material science processes, which we don't want to focus on right now. But idea is that you allow it to solidify. We call it curing. Right? So you allow it to cure, and once it is cured, if it is cured without a magnetic field, you get isotropic material. If it's cured in the presence of magnetic field, you get anisotropic. You get chain-like alignments, right? So this is the way you manufacture these materials. And then comes the question of, I want to use these materials and design something, right? So if you want to design something, you need to understand how they work, uh, uh, right? And to understand how they work, you need to model them properly. So there are various aspects of modeling this magneto-mechanical coupling, and these are the four topics I want to just talk about today. Okay, so I'll just quickly talk about how these Maxwell's equations of magnetic field arise and they couple with continuum mechanics problems. Then there is something called as variational setting, basically which allows you to do finite element modeling. For example, it allows you to do stability analysis. It allows you to do a lot of things. So it's very very general, which we'll talk about a little bit, and then we'll talk about large deformation, instabilities in these materials, along with thin structures. Okay, so so now let's focus. Having this introduction with us, let's do a little bit of mathematics, which is absolutely essential if you want to model this magneto-mechanical coupling. Okay, so so first of all, for I assume that not everybody is familiar with continuum mechanics, and that's absolutely fine. But the way we do this is through continuum mechanics, right? So I think that's something that is an essential aspect of what we're going to do in the future. So the idea is, if you already have familiarity with continuum mechanics, what you have is you have a body in its reference configuration, and it undergoes super large deformation, and it becomes this, right? So you can link all the points in the reference body to the current body. You've got something called a deformation gradient, which is F here. And within the continuum formulation, you also need to put in some form, you need to put in the magnetic field, magnetic induction, and magnetization. So these are three vectors that are always present in when you have magnetic problems, right? So you've got magnetic field, induction, and magnetization, and then of course you need to somehow link that to deformation gradient and the total stress. Uh, the main difference, if you have been doing just mechanics or just elasticity or just continuum mechanics, the main difference in the classical approaches and what we do in this multi-physics problems is that now the magnetic field lives everywhere. It's present inside the body. It's also present outside the body in the vacuum. So you need to have your equations properly so that it exists everywhere. And I think that is something that needs to be taken care of properly, right? Uh, I heard some sounds. So if there are any questions, please let me know. I can go over things. Um, right. So how do we do that? I mean, first of all, we need to write down properly our field equations, right? So Maxwell's equation is something people might have seen in physics earlier. The same equations arise here. You've got B. So small. The convention that I follow and many people in this field follow is that all the small alphabets are for fields that live in the current configuration. And all the capital alphabets, like capital B, are for fields that live in the reference configuration. Okay, so this is what the convention is that we follow. So this is the Maxwell's equation that you have. Divergence of magnetic induction is 0, and curl of magnetic field is 0. And this B union B prime means it's valid everywhere, inside the body and outside the body. Now, one like cool, one important thing that we need to do is, especially if you want to do any finite element implementation, or you need to do proper calculations, is that uh, you need to shift the reference configuration on the reference body. So you can have all the differentiation. So divergence and curl here, they are differentiation operator, right? So differentiation with respect to some XYZ coordinate system. So now this divergence and curl in the first equation are with respect to this small x, and the small x is a position vector in the current configuration. But what we want is we want everything with respect to this capital X. Because when we do finite element implementation, we want our equations in the reference configuration because this configuration is static. You can keep on deforming the body and this configuration small b keeps on changing. So we don't want our fields with respect to this small x. We want all our field with respect to this capital X. And this is one major thing I think that if you want to take away a few things from my talk, I think this is one thing you should take away is that we pull back all our equations into the Lagrangian form. So if you apply these transformations, so you from small b you get capital B, and from small h you get capital H by these transformations, then you get these the similar same equations, Maxwell's equations, capital D div B and capital curl H uh, in the reference configuration, right? And another important thing that arises is that not only that your body has deformed going from let's say one configuration to the other, the surrounding free space also deforms. So not only you have B union B prime, you have B naught union B naught prime. So B and B naught is the body, and B prime and B naught prime is the surrounding space, and both of them undergo deformation. So, so when you do finite element implementation, you need to account for deformation of the body as well as deformation of the free space because of this deformation. Right. Uh, so that's one of the key things that we should follow. Right. So these are Maxwell's equations. Then of course you get the usual equations that come from nonlinear elasticity, but they're modified a little bit. So this is a very standard equation, balance of linear momentum. It says divergence of some stress plus body force equals 0. And in this case, this P is the total first Piola Kirchhoff stress. And I just like to kind of again remind or maybe highlight for people who are still learning continuum mechanics is that when you work with these nonlinear problems, you can have many different measurements of stresses. So you can have some stress. So for example, this Piola Kirchhoff stress or the first Piola Kirchhoff stress is something that that has it's a tensor, and it has one leg in BR and other leg in B. So it's a strange tensor that kind of lives in both of these configurations. You can also have Cauchy stress, which lives entirely in the current configuration. You can also have second Piola-Kirchhoff stress that lives entirely in the first configuration, in the reference configuration. So I think you can write your equations in any way. I prefer to do this in first Piola-Kirchhoff stress because it's quite neat. The equations come out nicely, and it's also good for a finite element implementation. But remember, this is total first Piola-Kirchhoff stress, which means that the stress is something that accounts for forces, right, inside the body. So there is magnetic field as well, and there are some forces that are because of magnetic field. So this total stress includes both the mechanical and the magnetic forces. Uh, so this is super important because it kind of takes coupling into account. Uh, and similarly, you can get total Cauchy stress, which is a symmetric stress tensor, which lives entirely here. Okay. Right. So you have these. You have got the Maxwell's equations. You've got balance of linear momentum, and then comes, okay. There are too many things here. We'll go slow here. The important thing comes is constitutive relations, which is essentially how do you describe the material that you have, right? So you can have some sort of rubber. You can have, let's say, VHP. You can have silicone rubber. You can have natural rubber. All these rubbers have their own different properties. You can put in iron particles, or you can put in permanent magnet particles. You can put in steel particles, and then all these fillers might have their own different properties. So I think you need to have some sort of relationship that can describe material properties, and this is what constitutive relations are. Uh, and in this case, we are going to just focus on quasi-static magnetoelasticity, which means that we ignore any viscoelasticity, we ignore dissipation, we ignore any rate dependence. We look at the simplest possible scenario where there is elastic deformation and there is magnetic field, and everything is reversible. So if you want to model something very very simple like this, we can do it in the form of this energy density function W, which is a function of the deformation gradient and the magnetic induction, and you get very simple relationships for the Piola-Kirchhoff stress and magnetic field. Just differentiate W with respect to F, you get the first Piola-Kirchhoff stress. Just differentiate this W with respect to B, and you get the magnetic field. So these are relationships, and these relationships essentially describe material property. So everything about material property is captured inside this energy function, which is something like stiffness and the Poisson's ratio. All those things are captured in this energy function. And then there are some mathematical techniques from again coming from continuum mechanics, that if you're working with objectivity and isotropy, instead of F and B, you can have six invariants which have this property. So if you I think this is something, if you know about this, it's fine. If you don't know, just know that you can simplify the energy density function. And one of the examples that people very commonly use is having a Mooney-Rivlin type energy function for the elastic part and some linear terms for the magnetic part. But there are many different types of this W. This is just one form of W here. Right. Uh, okay. So if you have, so these three slides essentially contain all the equations that you need. And then if you can solve these equations properly, uh, then you're done, right? So I mean, but the thing is, all these equations are very complex. They are partial differential equations. They're nonlinear. So solving them is quite a difficult challenge. So we have done some progress using some open source software to work on these equations. You need a finite element framework because they're partial differential equations. But what I also do, or many people do, is if you want to just study physics of certain systems, you can simplify you can simplify the geometry, and to such a large extent that sometimes analytical solutions are possible. You can simplify the geometry sometimes that your all the partial differential equations simply become ODEs. And solving ODEs is okay. It's easy. Uh, another thing that often comes up is that when you solve these equations, you essentially get some solution for the body's configuration, which is an equilibrium. Basically, the shape of the body that exists under different forces, it's an equilibrium, and that equilibrium can be either stable or it can be unstable. And think of something like buckling of a column. So I think all of you might have. If you're in this mechanics conference, I'm sure you must have done some courses in your first second year about in mechanics about beams and columns and buckling of beams and buckling of columns, and you know about that as some sort of instability. And this is exactly the kind of instability we have here. That sometimes equilibrium can be unstable, so you can have a state which suddenly changes its mode. But in the case of soft materials, soft solids, this equilibrium can be desirable. In the traditional mechanics literature, you have columns of steel or concrete, and as soon as you have instability, you have failure, and which is something that you always want to avoid because you don't want your steel rods to buckle. But in the case of soft materials, all of that buckling, that instability is reversible. You can remove all the forces, and the rubber material comes back to its original shape. So that instability is not like something that causes failure, and this is what is very nice idea here, that you can use instability to your advantage. You can create certain aspects of your robotic systems based on instability. Uh, so uh, let's look at an example that I want, which is a very classical example. It has been, I think, people have been working on this example for 70 years or more, which is surface stability of a space, of a half space, right? So you have a very big block of material. It goes to infinity in the bottom dimension. It goes to infinity in left and right, and you've got a surface on the top. And what happens is if you compress it, so if you do this compression, basically compress it from left and right, you get these some sort of wrinkles. And this is a very well-known instability in nonlinear elasticity. And we can look at an example that how does this instability change if we introduce a magnetic field which is perpendicular to the surface or parallel to the surface, right? So this is, let's see, we can see an example like that. So if you want to work on an example like that, again, you need to go through a little bit more mathematics, but we'll see that it's not that difficult. Uh, that mathematics, I'm going to only going to present the ideas. I'm not going to go through a lot of detail. Right? So the idea is the following: you get some total energy of the system. So the total energy is energy that is stored inside the body plus energy that is stored outside the body in the free space because of magnetic field. All of that energy together, right? And uh, so this is like coming concepts coming from calculus of variations. If you have taken a course in finite element, then you are might be familiar with this. So when you have this total energy and you take the first variation of energy, put that to zero, that results in equilibrium equations. So these are the equations that we saw earlier, Maxwell's equations, balance of linear momentum, and so on. You solve those equations, you get an equilibrium state of the system. Now you want to check whether that equilibrium state is stable or not. And that check is given by this second variation of energy. If the second variation of energy is positive, then the system is stable. And as it becomes zero and then it becomes negative, it means that you have reached a bifurcation point, which means instability is going to appear now. And this is the bifurcation point I've shown in the slide. A very simple schematic here. So you might have some loading parameter. This can be, external force. It can be a magnetic field. It can be anything. And let's say as you keep on changing the loading parameter, you keep on moving along some solution. So you might have some state of the system, and that state might continue here, right? You probably might have. Let me move this. This path here, let's say solution path, is a very nice path for an equilibrium state. But what happens is once you reach the bifurcation point, when this second variation becomes zero, uh, the second variation is positive along this path, it becomes zero here, and it might become negative there. So as soon as the bifurcation point arises, you may have existence of multiple solution, and your system might move into a different direction. So even though the mathematics says that this is an equilibrium solution, it might not be physically achievable by the system because the energy is no longer minimum here. Energy is minimum along some other path, and that bifurcated solution may look completely different. So this is what I had in this example here, that you may have an extremely flat solution, which is let's say the principal solution, and after bifurcation you get these wrinkles because this is what kind of minimizes energy, and this is what I'm trying to demonstrate by this graph, right? Uh, so that's the basic idea, that you think in terms of energy. We always try to think in terms of energy. That and it kind of leads to very intuitive understanding of things. Okay, how do we solve this problem then? There are too many things in mathematics that happen. You can ignore this slide if you basically want to. mm, but the idea is that when you take second variation, you get some incremental equations, which is essentially equations for the perturbations. So I'll go back to this graph here. So what you try to do is you pick up any state on the principal solution, and you say, okay, if I move a little bit in some other direction, so instead of moving along this path, if I move a little bit, let's say in a different direction, do I do I still get a solution? Do I still get a valid solution? And you keep on checking that everywhere. And as you keep on checking it everywhere on this principal solution, as soon as you hit the bifurcation point, you will find a path which is possible, right? And that's how and that's when we say, oh, bingo, we found it. And that's where we say, okay, this is where the instability will appear. And that's the central idea, that throughout the principal solution, if you keep on changing your solution slightly a little bit and keep on checking whether a valid solution exists, and a valid solution exists at the bifurcation point, right? So now we can put all that into mathematics and say, okay, let me I've got some f and b. Let me look at some very small changes in f and b. So f dot and b dot are very small changes in f and b, and you essentially do those small changes. You go through the entire mathematics and you check whether a valid solution exists or not, right? All this is basically just to check whether a valid solution exists or not. Right. So in the case of the surface problem that we had, a valid solution, again, you don't need to go through all the content on the slide unless you are an expert, but essentially you can simplify your equations for 2D problem using these concepts. Uh, this is what is, I think you can see. So when you think of a valid solution, you want to look at a solution that is sort of sinusoidal along the x1 coordinate and exponential along the x2 coordinate. Okay, so why do we do that? Sinusoidal along the x1 and exponential along the x2. So let me go back to this picture again. See, along the x1 direction, as we move along the x1 direction, we've got wrinkles which are continuously sinusoidal, and they go all the way from left to right. Right? So we need a sine wave or a cosine wave along the x1 coordinate, but we also want that these perturbations, they are restricted to the surface. As we go down below, we want them to very quickly become zero. So they die down very, very quickly, and there is nothing, no perturbation at the bottom. So this is what we uh, do by using this form of solution. So you have an exponential along the x2 direction, which means x2 is a vertically downward direction. So it just dies down very, very quickly uh, as you go down below. But along the x1 coordinate, you have sine and cosine, so it kind of keeps on oscillating along x1 coordinate. So you are looking at solutions like this, and you want to check, do these solutions exist at some point during the deformation cycle? And if they do, that's when bifurcation happens, and that's when instability starts to appear. So
Binayak
if you do,
thematic numerically.
sorry, could you please repeat that?
Okay, no, no, no. Actually, he has not muted his mic.
Okay. So let's continue then. So if you do all that correctly, and again, you can see the papers to look at the details. Uh, Let me quickly show you the result. So this is the result from a recent paper. Actually, it was published only last week, and this is the first time I'm. No, this is the one that was published earlier this year. Uh, so let there are too many things going on here. Let me show you things a bit slowly. So first of all, on the horizontal axis, we have got the strength of the magnetic field in some dimensionless format. So this is all uh, no dimension. On the vertical axis, we have got lambda, which is the amount of stretch for the half space. So when there is zero magnetic field, you have a value which is very well known in literature, 0.54. And this is, I think this number is well known since last 70 years for elasticity. So what it means is that if you keep on compressing the half space, and when you hit, so you start at 1, you keep on compressing, and when you hit this number 0.54, that's when you would start seeing those wrinkles on the top surface. And then let's pick up any graph. Let's pick up this red graph. Okay. So red curves corresponds to some value of beta. Beta is a material constant. Alpha is a material constant. They don't matter right now for our discussion. What matters is uh, this red graph, and as you move along here, you see. Let's look at this point here. Okay. So this is close to let's say magnetic field one. So when you are at magnetic field one, you are at somewhere at this point here. And it means is that when you start at one, you keep on compressing, so you keep on going down, you hit this graph very, very quickly. Instead of going all the way down to 0.54, this is somewhere close to 0.9. So the wrinkles start to appear very early. So you don't need to compress it as much. You can see wrinkles very, very quickly. In fact, when you apply magnetic field, very large magnetic field, you would see that you don't even need to compress it anymore to get those wrinkles. The magnetic field itself just starts creating wrinkles on the top surface. And in fact, you need to stretch it. You need to, so anything lambda greater than 1 means it's a tensile strain. Lambda less than 1 means it is a compressive strain. Okay. So compressive strain typically causes instability and wrinkles. Uh, but in the case of this red curve, for large magnetic field, you need to apply a very large tensile strain just to make sure that there are no wrinkles. As soon as you fall below a certain level, wrinkles start to appear. So magnetic field has a tendency to create those wrinkles inside the body, right? So let me go back to this sketch here. Uh, so when you have perpendicular magnetic field, these wrinkles will appear no matter what you do. Uh, so you need to this is something that is useful. And even though these results are something that we are showing you numerically, this has also been observed experimentally in certain papers. And then you can play around with alpha and beta, all these material parameters, and you get all sorts of curves, which shows that this behavior is essentially nonlinear, uh, right? And then there are many other things going on there, which we can ignore for the moment. The idea is that you can induce instability just by applying a magnetic field. And then this was magnetic field when it was perpendicular to the surface. You can also have a magnetic field which is parallel to the surface, and then it gets similar but different behavior. You start again at 0.54, and then you move along in different directions based on what the material property is. Okay. Uh, there is also a very, very common variant of this problem in which you apply a layer on top of the surface. So on the half space, you put a layer on top of it, and then the problems become really, really rich. So you get a lot more parameters to play with. You have the high stiffness of the layer, which is mu u. You get stiffness of the substrate, and then now in addition to this critical stretch, which you were looking at in the previous graph, you also get a wave number. Uh, and then you have to look at both lambda and you have to look at k at the same time. And you need to find out what is the optimal lambda and k for your problem. Okay? So again, we can do that. The mathematical principles are quite simple. The physical implementation requires a little bit extra things. But what you can see is that uh, what I've plotted here is in addition to for all the different possibilities. So you have mu u over mu s. So the layer is generally stiffer than the substrate. So that's why this is always most of the region is greater than one, because the region less than one is not interesting from a mechanics perspective. The region greater than one is interesting. You always typically have a stiffer layer. And as the layer keeps on becoming stiffer and stiffer as you move in this direction, you see that the lambda critical increases, the blue graph increases, and the red curve decreases. So lambda critical increases means that you need less compressive strain to induce instability. And this was a purely mechanical problem. There is no magnetic field here. If you put in magnetic field, you obviously change the nature of this graph. So again, the central idea is that the nature of the graph changes. There are too many material parameters here to kind of go through in detail each one of them. This paper was published just last week. You can have a look at this. It's available online. All of my papers are open access. So if you just log on to whatever Elsevier, and you'll see that you can easily download and see the mathematical details. But the central idea is that you can change the nature of instability by applying a magnetic field, and then you can switch off the magnetic field and you go back to the elastic problem. So if you link it back to the original videos that we showed about those robotic systems, you can switch on and switch off the instability, so the different deformation modes, just by applying the magnetic field or removing the magnetic field, or changing the direction of magnetic field, or changing the strength of the magnetic field. And you don't need to have any physical system attached for applying more strain and so on. Okay. uh, right. uh, I also want to spend a little bit more time on looking at membranes or thin structures. And this has been a research area for many years now. So the previous example was for a bulky solid. Uh, Bulky solids are easy to model, but also they typically are not preferred in manufacturing because they require a large amount of magnetic field to activate. But if you have a really thin structure like a membrane or a shell, then you can apply smaller magnitude of magnetic field and you can create any actuation or deformation, right? So, and there are a lot of interesting instabilities that appear in membranes. So look at this, a very simple balloon from birthday party of my son. And you tie a knot, you inflate the balloon, you tie a knot, and you see there are regions where you have wrinkles. And these wrinkles appear because of compressive strains that happen in the membranes. So what happens is, in bulky solids, you can compress a bulky solid, and it maintains its shape. But membranes, they do not have any bending stiffness. So if you try to compress a membrane, it will immediately wrinkle. Think of like a cloth of a shirt. If you can stretch the cloth and it will give you some resistance. But if you try to compress the cloth along the surface, it will immediately buckle or wrinkle. It will not offer any resistance because membranes do not have any bending stiffness. So getting wrinkles in membranes is very, very easy. uh, there is another kind of instability in membrane called a limit point instability. And this is often observed during inflation. So if you plot the pressure and the volume graph for any membrane in general, you would get a graph like this. Uh, and this is what happens. This is called as a limit point. This here that if you keep on applying pressure, you would see there is a jump uh, at this point, and then you move along this path. So this is called a snap through. That a lot of membranes just snap and just have a very rapid increase in their volume as you inflate the membranes. So we have seen this or modeled this aspect of membranes for magnetic solids. And I'm conscious of time, so I'm not going to focus a lot on maths. I'm just going to show you some basic ideas. Uh, so we can pick an example. Let's say an example of the toroidal membrane. And let me show you some ideas, some key things that happen here. So when we model this limit point instability for a membrane, this is what we observe. We In the presence of magnetic field, we get an extra limit point, and that is due to essentially magneto-mechanical interaction. And many people in the early stages, we saw this and we thought this is a numerical instability. This is a very sharp thing that happens here. But then we dug in a lot more deeper and we realized this is a physical instability that is present in magnetic materials. So you get two limit points, not just one. And for very large magnetic field, this red curve, everything goes downhill, so there is no stable state really. When it comes to wrinkling, let me spend like 1 minute here. Uh, Wrinkling is a very, very interesting problems in membranes, and it has been kind of studied for many years now. many decades now, in fact. Uh, but the central idea is what I said in the beginning, that membranes cannot resist compressive strains. They can only resist tensile strains. So when you have your energy density function, let's say lambda 1 and lambda 2 are the stretches in the two directions of the two, you've got 2D membrane, so you've got two directions, you've got lambda 1 and lambda 2. As soon as one of the stresses becomes negative, you need to modify the energy density function. And this is called as tension field theory. Uh, this is called as a relaxed energy density function. And of course, I'm not going, don't expect you to learn all of this just now, but maybe you just look at our papers to see the mathematical details. But the central idea is that membranes do not resist compression. So when you have an energy density that is based on lambda 1, lambda 2, you need to get rid of one of those things when you have compression in one of the directions. So you need to kind of modify the energy density function so that you account for the fact that you don't store any energy in compression. There is no elastic energy being stored when a membrane is compressed. It can't offer any resistance, right? So that's the main idea to model wrinkling. And the I mean, I'm 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 going to skip a lot of results here. They're not super important in terms of presenting the ideas. I'm going to spend one more minute on this slide. Again, it's a bit more mathematical, but just to make you aware that there are these techniques as well. So in calculus of variations, uh, we try to check the stability of any equilibrium by looking at second variation. So you can have total energy in terms of, here I've used pi. So this capital pi represents total energy. And then second variation is something that you want to check to make sure that whether the equilibrium is stable or not. And checking the second variation is a very, very difficult task. In all of finite element method, people use a very simplified approach, which is they check only the necessary condition, but they don't check the sufficient condition. So there is a necessary condition attached to it, there is a sufficient condition attached to it, and people simply check the necessary condition. So which is a matrix have being positive definite. So you might have heard of, if you have done FEM, you might have heard of stiffness tensor, stiffness matrix, and checking whether the eigenvalues are positive. So this is exactly corresponding to this necessary condition that all the eigenvalues are positive or not. But then there is a sufficient condition as well, and there are certain problems, and this is one of the things we identified early on, is that you can have a problem where you have some equilibrium here, for example, where you have a both the necessary and sufficient conditions are satisfied, so the solid lines, and you are sure it is stable. Then you've got these dotted lines of equilibrium where the necessary condition is not satisfied, so the eigenvalue is not positive, and you are very sure it is unstable. Then you have some intermediate states where the eigenvalues are positive, the necessary condition is satisfied, but the sufficient condition is not satisfied. And these are the cases where you cannot be sure. Traditional FE framework will tell you, oh, this is stable, but a mathematician will tell you we don't know because the necessary condition is satisfied, the sufficient is not satisfied. So this is something again quite important to be aware of, and just something you should know. Right. So let me stop here. I think this is just on time. So to summarize, we talked about multiphysics coupling and large deformation, and I presented some idea to model stability using variational principles in bulky material and in thin membranes. Uh, but I think from the point of view of this workshop, I'd just like to emphasize that this is a field which is still very new in many ways, and we are just getting started. And there are a lot of open problems, and three main domains you can think of is one is around how do you apply these new materials in the areas of soft robotics and actuators and devices, and how do you kind of engineer new things. You can think of application in space science, in biomedical science, in many other in sports science, in automobiles. There are a lot of possibilities where you can apply these ideas. Then coming more into, let's say, the modeling itself, the mathematical models are very nice, but doing a numerical implementation using finite element is quite challenging still, and people have been working on them for some time. And I think this is also a good space to get in if you are interested in numerical methods, computational mechanics. You can. There are many problems in this area, and then there are a huge amount of open questions about what is the exact material property, what is the exact material behavior, and how do we experimentally quantify those things? How do we get proper data? And that's another open problem that's there. And with that, I'd just like to stop and see if you have any questions. Thank you so much for listening.
Yeah, thank you, Professor, for a nice presentation, and it is very enlightening, informative, and quite interesting. So the floor is now open for uh, questions. Please, if you have any question, please ask Professor.
Good afternoon, sir.
Hi. Yeah.
Good afternoon, sir. Sir, as you discussed during your presentation, to increase the magnetoelasticity property, we can add the iron particle or ferrous particle in the elastomeric material, right? So by adding the iron particle or iron particle, can we get the homogeneous mixture?
Okay, that's a very good question. Let me quickly go back. So let's say we are talking about something around these slides, uh, and you can see here uh, when you do this. So I mean, this is a very basic. Can you please mute your mic? Sorry, there's a bit of feedback.
Okay, sir.
Uh, so as you can see in this sketch, essentially, you need to uh, you need a mixture of, let's say, matrix material, the elastomer liquid, with some particles which can be ferromagnetic or magnetic, with some additives, and you need to have a very efficient mixing process and then a curing process. So it needs to be cured. And you're absolutely right. One of the bigger challenges in doing this is to get a homogeneous mixture. So what happens is these particles, they have a tendency to kind of clump together. So they form these big agglomerates. This is what we call. And then uh, there are certain coatings that can be applied to these particles to reduce that agglomeration, but that agglomeration still happens. The other problem is gravity. So when you have these particles, and if the curing takes a lot of time, they would tend to like kind of fall through the liquid due to gravity and down below, right? So again, this would lead to an uneven distribution. Uh, and of course, there are certain challenges. So if you apply magnetic field, they would anyway make these chains, but these chains will not be like they may have another kind of secondary effects, and they make again collapse onto each other. So I think your question is absolutely right. It's a very challenging problem to solve efficiently. People have been working on this, obviously. So the slide that I showed in the previous was from 1996. So people have been working on this for almost 30 years now. And through these various techniques, like let's say coating the particles properly by reducing the curing time, by mixing it in a way that the liquid mixture, you start with a very homogeneous liquid mixture and then you remove all the gases. People you tend to achieve an isotropic homogeneous state, but yes, it's difficult. Absolutely true.
Sir, is
Okay,
there
any
no
other
any
question? Yeah, please, please.
Sir, still is there no any method from which we can get a homogeneous mixture?
Oh, I mean, you can, of course. So I think the idea is how homogeneous. So there is no 0 and 1 here. There's always a degree of gray. Uh, so by applying, so I'm first of all, I'm not an expert in manufacturing, but I think by having appropriate coating on these particles, by having certain nano particles as additives, you can make sure that they do not form agglomerates as much. You can make sure that there is very little gases present inside the mixture. So you can do that, but I think it's always a degree of homogeneity. So you will not have a very homogeneous distribution ever. I think it's always about how close you are to that homogeneous homogeneity, because in computational methods we can always assume certain ideas, but when you actually manufacture something, there will always be some certain imperfections. So yeah.
Okay, any other question? Yeah, then I'm having a few few questions. Like you talked about the sufficient condition and the necessary condition.
Yes. Into
So
that slide.
so is it related to somewhat? Yes, yes, it is related to actually this condition is for the stability. The necessary condition is talking about the positive stiffness.
Yes.
Uh, yes. And regarding the sufficient condition, what is the philosophy behind it? So, for example, from a layman's language, is it the dynamic it is talking about?
So to be honest, I can't link to a direct mechanical equivalent here. Uh, w- uh, for let's say for simple problems in linear elasticity, and bulk bulky problems in nonlinear elasticity, the necessary and sufficient condition typically collapse. So they typically become the same thing. So for example, if you have a you're working with Lame's constants in linear elasticity, and
Yes.
write down this energy density function, you would see that these two kind of become the same thing. So simply checking the stiffness matrix and checking the eigenvalues is sufficient. That's okay. And this is what people have been doing for many decades. But I think when it comes to more complex nonlinear equations, like what we have in multiphysics coupling and what we have in membrane mechanics, then these conditions are kind of different. So necessary condition is still positive definiteness, but this is not directly linked to the stiffness matrix. So this matrix P is not your CIJKL. It is
Hmm.
it contains terms coming in from pressure as well in the case of membranes. In the case of magnetic coupling, it contains terms coming in from magnetic field as well. So it's slightly different than the traditional CIJKL. So this has the same flavor, but it is distinct. And I think this is something that we discovered. I mean, not discovered. I mean, this is very well known in the field of mathematics for centuries, for at least a century. But for from field of mechanics, not many people have a look at this
Okay.
carefully.
Okay.
I think we should just be aware of the fact that these exist, and for certain problems, these are important.
Okay. Yeah. Nice. So any other question, please? So if not, then let's all of us thank Professor for his wonderful talk. And thank you, Professor. So
Thank you, sir.
we'll be concluding this part. And our next session is going to start from 4:15, and Professor Deepak Kumar will be our speaker. So
Hello, sir.
thank you, Professor.
Thank you so much for having me, and it was a pleasure giving this talk. Yeah,
Thank you, sir.
and thank you
Thank you.
for listening. I hope you were not bored after lunch, but
No, 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 sir. Everybody has enjoyed it.
yeah.
Thank you, sir. Thank you.
Thank you, sir.
Okay, see you then. Bye.
Thank you. Okay, good afternoon, everyone. So let's welcome Professor Deepak Kumar, our speaker for this session. So, Dr. Deepak Kumar, am I
Good afternoon.
audible?
Yes,
Good
sir.
afternoon.
You are audible.
Good afternoon. So I think I have introduced to you the brief introduction about Dr. Deepak Kumar. And so without wasting any further time for introduction, we'll be just moving to the lecture. So now, Dr. Deepak Kumar, the stage is yours. So please.
Okay. So thank you, sir. Thank you for giving me this opportunity to deliver my talk to the audience. So first, I would like to know that little bit noise is coming from my side, or it is fine. Actually, right now, some cutting is going on right outside the room. So
It is all
not
right,
so
I
much
hope.
noise is coming.
No. It is all right.
Okay, fine. So let me share my screen. Okay, so please confirm my screen is visible to all.
Yes, sir. Yes, sir.
Okay, so once again, thank you, Professor Sarangi, for inviting me for this, inviting me in this workshop. That is workshop on smart polymers and electromechanical applications. So basically, in this workshop, I would like to discuss more or less introductory things about the soft active materials, and the topic of this talk is means I have mentioned here, just also they are shared with you by Professor Sarangi. So we are going to discuss about the soft active materials based actuators, and specifically we are going to discuss how we can design and fabricate such actuators. So for that, I hope so. I would like to means after the talk, you will be getting the knowledge about the soft actuators, what soft actuators are, and what are the different type of smart materials actually we can utilize to develop these type of actuator or to fabricate these type of actuators, and particularly these type of actuator where we can utilize. So specifically means in the previous talks we have discussed means various professors have discussed. So specifically these soft actuators we are going to utilize in the field of software robotics. And later on, after the introduction about the smart materials, soft actuators, we will discuss that how we can fabricate. So we will see few examples that particularly means we will see the dielectric elastomeric material based example, how we can fabricate these D-based material soft actuators. So these are the means goals for this talk. So come to the first goal. Let's discuss about the introductory things about these smart materials, soft actuators, and how we can utilize these actuators in soft robotics related applications. So before moving ahead, I would like to discuss, or I would like to take your attention towards the what are the different type of technological revolution we have from our history perspective. So typically, we can categorize our human revolution in three different categories. Like the first one, we can name it as a industrial revolution. Typically, we can say that it happens in between 1760 to 1840. And here, in this type of uh, human revolution, we have got various kind of various types of innovations, like particularly for uh, automation, mass production, and rapid transportation related innovation we have seen. So here you can see various pictures, like we have got the engines, we have got the industrialization. So various industrial related innovation we have seen in this first human revolution or industrial revolution. So coming to the second one, second human revolution that we have named it as the information revolution. So typically we have seen this type of second human revolution or information revolution in between 1940 to 2010. So here major outcome was the internet, computers, mobile phones. So basically here we were going to utilize the internet or to flow the data from one place to another or free flow of the information, and how we can smartly utilize the data, and not particularly related to the information technology. So we can also utilize various, multiple type of different domain related datas, transportation. So here you can see the big pictures like big computers. Previously, we were having very big size computers, and later on in our childhood days, we have seen this big size smart monitor. Sorry, big size monitors, and then mobile phones, and later on. We have started seeing the development of the mobile phones, screen mobile phones, tablet, laptop. So this particular second information revolution dedicated to the computers innovations and internet innovations. Now coming to the third one, that is the that we have named it as intelligence revolution. So here you can see that we can see that we can say that it has been started since 2010 onwards, and we can say ourselves also means we are also the part of this type of third human revolution currently ongoing. So here what exactly we are doing? So we can say that whatever the forefather scientists we have means they have developed various different type of machine, different type of computers, different type of whatever the things they have developed. So now means with the development of the existing machines, and also from the second human revolution we have the computers, we have the information technology development. So now we are going to somehow merge them together, and we are making the existing machine smarter. So that's why we come up with this very well-known adjective, intelligence. So we are making our existing machine more intelligent. So now that's why we have named it as intelligence revolution. So particularly we are developing very smart robots. Whatever the previous robots people have developed, now we are making them very smarter, or we are making them very more means we are developing them in such a way that they can perform better whatever the previously we are having the developed robot. So in such a way we have divided the human revolution in history perspective. So now coming to the topic that what are the smart materials and why they are needed. So in the previous talks, professors have given you different type of smart materials introduction. So I'm just going to recap the things. So what is smart materials? Why we are putting this word before the materials is smart. So as you can say that materials are well known, like particular scientist or particular field of person, they are going to utilize to study the system. They are going to, if they are interested to make the physical system, so they have to choose any kind of material. But we are focusing particularly on the smart materials. So let's take very simple example to understand what smart materials are. So suppose any material you are having, so if you are going to apply any kind of load, so it can deform, right? But when you are going to apply the load, so particularly if you are going to apply the mechanical load, so it is going to deform. But we are not interested to apply any kind of mechanical load. But without applying the mechanical load, if the material is going to give you any kind of deformation, so in that way we are going to say the material is smarter. Or so, but to get the deformation, we have to apply any kind of force field. So the force field initially, which we were applying the mechanical, now we are going to change that field in terms of the electrical or any means magnetic or any kind of chemical or any kind of field forces we are going to apply to get the deformation. So now typically, let me tell you the importance of the soft active material, because there are multiple type of materials, but we are preferably focusing our attention towards the soft active materials. So let me tell you what is the importance of the soft materials. So here you can see the pictures, like let's say I'm giving you some example. So why people are shifting from the conventional robotics to the soft robotics? So let me tell you that in the recent time, or before that, let me tell you, suppose you want to purchase some kind of toy for your a baby, a simple 6 month old baby. So for that one, whenever you are going to market to purchase some kind of toy, so your first preference is to get the, to purchase the toys made of very gentle kind of, made of rubber type of, toy made of rubber materials. But you cannot purchase a toy made of typically metals. From made of metals toy, you just you are not preferring that one. So the reason behind is that you are actually putting your attention toward the human safety, because ultimately you are having the concern that your baby should not getting any kind of harm. So in that way, you can say that the soft material is having very much importance in your life. So right now, people are slowly shifting from the conventional robots, which previously people have, people were developing, or to develop the conventional robots, people were utilizing the hard material like plastic, metals, and now slowly people are shifting to the soft robots, which are made from kind of softer material, just like you are getting the inspiration from the nature, because nature has also made our body, human body, means with the help of tissues, and they are more or less look like the polymeric material or kind of rubber materials. So they are more kind of closer to the soft materials. So in that way, we can get the motivation from the nature that we are slowly shifting from conventional robotics to the soft robotics, to closely mimic the natural system or natural robots. So now coming to the means smart materials. So as we have discussed that to get the deformation, typically we ignore the mechanical deformation, or sorry, mechanical loading. So in order to get the deformation, we require some additional type of force field. So we are going to use either electric field or magnetic field or any kind of chemical field or some kind of temperature field we are going to utilize as a cause, and as an effect we are getting the deformation. So we can say that in a simpler way to define the definition of the smart material. So any kind of material that changes their elastic behavior with application of any electromagneto or any kind of electrical, magnetic, or any other kind of field, they are going to get the deformation. So we have named it as a smart material, or kind of electromagneto active material also we have referred sometime. So of course, they are having the lighter in weight, of course, smoother in application, and of course, safe. So we can interact very gently, instead of interacting a hard metallic based robot. So, but on the contrary, whenever you are dealing with the soft active materials, so you have to deal with the non-linearity. So whenever you are going to apply any kind of loading, so the deformation you are getting in a, load and deformation relation, you are getting a very non-linear. Instead of you are using the metal, so somehow metal in some range you can get the linear relation between the load and deformation. But whenever you are dealing with the soft material or soft active material, you have to deal with the non-linearity starting onwards from the initial initial state onwards, you are getting the non-linear deformation. So using these smart materials, so simply we can say that yes, simple type of rubber, or you can say that not exactly the simpler rubber, or any special rubber, or any special kind of soft material which can give you the deformation, either application of electric field or magnetic field. Just like in the previous lecture also, you have seen magnetorheological elastomer. So here there you have seen that we have filled the magnetoactive particles, and with application of magnetic field you are getting the deformation. Similarly, you may have a kind of electroactive polymer, where you can actually fill the electroactive particles, and when you are going to apply the electrical voltage or electric field, so you are getting the deformation. So using such type of material, you can develop various kind of sensors, actuators, and with the utilization of these materials, you can actually develop these actuator and utilize directly to the soft robotics related systems. So now let me give you very simple example for such type of smart materials. So that is the very first or very commonly used smart material is the dielectric material. So how it is going to look like? So basically, a dielectric elastomeric material is a 3M BHB material. It is coming in the code of 4910. So there are other codes as well. So means other codes, meaning other codes is having different mechanical properties, like 4910 is having some it can show different properties, and if you are changing this code 4910 like 4905, so it can see give you some different mechanical properties or electromechanical properties, because this is going to give you the deformation. Even though you are not going to apply the mechanical force, you can get the deformation just by applying the electrical voltage only. So you can easily purchase. It is coming in the form of simpler tape. That's why it is also known as 3M BHB tape. And you can easily purchase from any commercial website, or sorry, any e-commerce website. So it easily you can order it. And here you can see that with the help of this tip, you can develop whatever the type of actuator you would like to fabricate. Like you can develop the plate-like actuator. So whatever the configuration you required for your system designing, you can choose that configuration. And using this step, you can actually develop such, you can generate the configuration. Like you want to develop the palm actuators. In order to do so, what you can do, you can take the, you can cut the sample from the tape, and you can have the plate-like configuration. So in that configuration, what exactly you have to make it? So to get the deformation, of course, the application of the electrical voltage gives you the deformation, but not exactly. Means you have to understand that how the arrangement of the system you have to take care. So for getting the deformation, what exactly we have to do it? Here you can see that we have taken the elastomer, and in upper side of the layer and lower side of the layer, you need to apply some kind of electrode. You have to make some electrode, and for that you need to apply some kind of carbon grease. So we will understand later for in detail. So here you can say that the black color we have applied here. So we have put it the carbon grease. So in that putting the carbon grease gives you the electrode, and lower side and upper side we have put it the carbon grease. And also to attach the voltage power supply, you have to attach some kind of very thin copper tip, and in those thin copper tip upper side and lower side, you will connect the wiring of the power supply. So after is doing all the things, what exactly you will get? So whenever you are going to switch on the power supply, here you can see the image. You are getting some kind of deformation. Means you are getting the thickness reduction, and aerial expansion in another dimension, or another dimension. You are getting the aerial expansion. So such kind of deformation actually is coming because what is happening inside. So basically this type of material has the electroactive particles. So, and whenever you are going to apply the electrical voltage, so what is happening, the some of the electron means the current is going to flow, so some number of electrons is going to go, or you can, the electron density is going to uh, coming to the one side of the layer, and another side of the layer, the positive charge density is going to develop. So in order to development of these two different charge densities, so in the thickness direction you are having the attraction force, or some kind of, you can say that Coulomb force is going to develop. So because of that, this attraction force, the thickness direction or thickness is going to reduce. Or sometimes it is also known as the Pellerin pressure, or kind of, Maxwell force also people have given the name. So kind of the things, you can say that even though we have not applied any kind of mechanical pressure, but still we are getting the compression in the thickness direction. So we can also means people have given the this PEL, means Pellerin pressure, we have given the name. And sometime you would like to make the configuration. Typically we make the configuration for muscle actuator development. So in order to do so, what you can do, you can take the same sample from the BHB tape, and you can roll it. And of course, to strengthen, or you can say that to enhance the means kind of mechanical stiffness, so sometimes we can put the nylon fiber to introduce the anisotropy in the actuator. So you can put some nylon fiber as well, and in addition to the BHP tape. So after rolling, you are getting the configuration just like you are having the muscle actuator. And again, you have to put the carbon grease coating, and then you will be having the two electrode. And again, when you are going to apply the electrical voltage, you will be having the muscle-like actuation. So in detail, we are going to see in the further slides. So different type of actuators we can develop with these with the utilization of the BHB tape or dielectric elastomers. So if we are going to define what is a soft actuator, so actuator is something, you can say that in simpler way, it is a mover or kind of actuator. It is getting some kind of energy or input energy, and that energy has to be it is going to convert, so that actuator is going to convert that input energy in the form of output motion, or in the form of mechanical motion. So that is the system of the actuator, that is the definition of the actuator. And here are a different type of actuators you can see in the slide. So from very simple case, you can see that we have taken a simple BHB tape, and in that BHB tape upper side again we have put it the carbon grease coating, and of course in the lower side as well. And when the means kind of power supply is to be attached with the help of the copper tape, and here you can see that. And suppose in the same BHB tape we have also attached one simple spring here. So as you can say that when the voltage is being applied, so the thickness is going to reduce, and because of the thickness reduction you will see the aerial expansion in another dimension, and because of that you are having the deformation in the spring. So in such type of actuation you are getting, this is the simplest case of the actuation you can get from this BHB tape or dielectric elastomer based actuator. This is kind of actuator where you can see the displaced you can get the displacement from the spring with the help of the controlled electrical voltage. And coming to the second, this here you can see that the muscle actuator we have prepared from the BHB polymer, or you can say that the dielectric elastomer. So again we have taken the BHB tape, and we have rolled it, and we have put it again the upper side and lower side the carbon grease. And again, here you can see that previously we have not applied the any kind of electrical voltage. So initially we have measured the length. So here you can say that the initial at 0 voltage some length is there. What in means whenever you are going to switch on the voltage or electrical voltage, so here you can again measure the length of this muscle actuator. And additionally, what we have done it in this muscle actuator means not only we are going to apply the electrical voltage, and in addition to that one, we can also apply, or you can say that some kind of pressure also you can supply uh, in addition to the electrical voltage. So here initially you are having 0 voltage and 10 kilopascal applied pressure state, and then you have switch on the power supply, and you have keep remaining the pressure constant like 10 kPa. You have not increased the pressure, and yeah, you have just only increased the voltage, and you have switch on the power supply. And later on you will observe that the actuation length or length of the actuator is going to change, and you can measure it with the applied 4000 voltage or 4 kV voltage. You are having the change in the length of the actuator, and you can measure it. And so with the application of this voltage as well as the pressure, you can control the actuation of this muscle actuator. So of course, you can utilize the two input system like electro-pneumatic control to get the controlled length of the actuator. Similarly, you can have this type of actuator where you can also you can sometime it is also sometimes required to ignore the electrical voltage control. So in that type of system, you are suppose you are going to utilize only the pressure, because the actually the reason behind this is that sometimes you may ignore the electrical voltage application, because if you are going to if you are going to design the system, and that has to be beared by the human body itself. So in order to do so, you sometimes ignore this means dielectric elastomeric related system, because the major limitation of this dielectric elastomer is the requirement of the high voltage. So you have to deal with the 4 kV voltage. That is not good for the the actuator which you are going to attach with the human body. So in that case, you can ignore, and of course you can still utilize the soft material to develop the actuator. In those cases, you can ignore the electrical voltage control, but at the same time you can utilize the pressure control only. So here you will see the example. Suppose you want to design some kind of gripper, and a human hand is going to wear that gripper, and that gripping you want to control with the applied pressure. So here you have ignored the electrical voltage control, because that system you are going to attach with the human body. But if you are not attaching with the human body, so of course you can utilize for the robot. So you can design both electro-pneumatic system. So you can control the system or actuator with electro-pneumatic control. So here you can see the some kind of spider-like actuator. Again, the actuation is going to control by the application of the pressure. And similarly here you are getting the you are having the picture that is known as the McEwen muscle actuator. So basically in this type of actuator, what we are having, so here you may have two different choices. You can utilize the pressure control, as well as you can also have the electro-pneumatic control. So you can have both of the choice depending upon the requirement. So initially, McEwen actuator had only chosen the pressure control to develop the muscle actuator. So to develop the McEwen actuator, what he has taken, he has just taken a simple rubber tube. Inside that the picture here you can see that, and in that rubber tube, and he has braided some kind of nylon thread. Here you can see that, and this braiding requires some particular angle optimization to get the optimized output. And the output, of course, you can get the output in terms of deformation. And if you are not restricting the actuation, then you will be getting the deformation. You can measure the actuation in terms of the change in the length. And of course, if you are restricting the side of the actuator, so you will be getting the output in terms of the force. So means you are restricting the deformation. So in that case, you are getting the output in terms of the blocked force. So again, the McEwen, so means you are applying the pressure from one side, and you are getting the means control. You are getting the out deformation. If you are not restricting the deformation, you are not restricting the deformation. So you are getting the deformation in the in the form of change in length. So, and parallelly, if you are going to apply the electropneumatic pressure both, in order to do so, what you have to deal is, previously you have taken the nylon tube, oh, sorry, simple polymeric tube. So that has to be replaced with the BHB type of polymer. So in order to get the electropneumatic system. So this electropneumatic system, where means basically, why, you can ask me the question, why this additional electric field control is needed. Of course, we can control this McEwen vessel actuator just by applying the pneumatic pressure. So sometime the requirement we may have in such a way that we require very fine tuning type of actuation. So in order to get the fine tuning, it is very difficult to achieve such fine tuning from the pressure control only. So in order to get the fine tuning, so we are going to include the electric field control or electrical voltage control also. So that McEwen muscle actuator can be, extended to the electro-pneumatic muscle actuator. So different type of actuators, I can show you different type of limitation. But as the as Professor Saxena has discussed you that the instability in the soft actuator sometime can give you the you can utilize the instability as a positive requirement. So the major sources of the instability, typically in the soft actuator, we use the wrinkling and different type of limit point instability, as the Professor section has discussed. So we can utilize these type of instability in a positive manner for different type of soft robotic related application. So these are the few actuators here. You can see that. So kind of you can design soft actuator with the control of either pneumatic control or voltage control. So you can design the gripper to grip the some kind of pen, and you can write from this gripper. And of course, this is the McEwen muscle actuator. So where you can see that with the pneumatic control, you may have the muscle-like actuation. And similarly, in this muscle-like actuation, you can also include the electrical voltage control. So sometimes you are having the fine tuning type of actuation. So in order to get the fine tuning type of actuation, you can utilize the combined form of electro-pneumatic, electro-pneumatic control in the actuator you can include. So again, the instability. So here there are, if you are talking about the dielectric elastomers, let's take a very simple example, the plate type of configuration. So when the instability is coming, or when you can observe the instability, so whenever you are going to apply the voltage, so at what state the instability will come into the picture. So Typically, as we have already seen or discussed, how the dielectric elastomer is giving you the actuation. So we are having the dielectric elastomer, and we have to form the electrodes. So two metal electrodes, we put the carbon grease in the upper side and lower side of the actuator. And of course, with the help of the copper tape, we will attach the power supply. And when the power supply is going to be switched on, so you are having the thickness reduction and aerial dimension, means aerial extension in another dimension you are going to observe. So here you can see that. So as the voltage is going to increase, after a particular threshold of the limit, you can see that in the image, you will be getting some kind of wrinkling. Wrinkling means kind of, suppose in the picture also. So initially, when you are switch on the power supply, the thickness is going to reduce. So initial onwards, you are not observing any kind of wrinkles, but after a certain time, means as the voltage is going to increase, so after a certain time or after a certain value of the voltage application, you will be observing the wrinkling. So basically, wrinkling is going to give you the information that either you have to stop, or still if you are going to increase the voltage, and then the actuator may actually break down. So basically, these are the, you can say that you can utilize this information to stop the voltage supply. So means to avoid the breakdown of the voltage. But sometime these type of wrinkling can be utilized as a positive manner. Suppose you want to design a kind of smart window. So these type of wrinkling can give you the such type of idea to design smart windows. So we have discussed about the actuator, and very simple type of actuator configuration we have discussed: plate type of actuator and muscle actuators. And let us discuss about the generator, means because we have discussed about the dielectric elastomers. So dielectric elastomers can also be utilized to develop the generator, also means generator as well. So what exactly you have to do it to actually develop the generator or to design the generator from the same dielectric elastomers. So previously, to get the to design the actuator, you were doing the initially you are going to supply the electrical voltage, and as an output you are were getting the deformation or mechanical deformation as an output. So the same idea, now you have to reverse the situation, and means now what you are doing it, you are taking the same system, you are taking the same dielectric elastomer, and again you have to put the carbon grease, you have to make the electrode upper side and lower side. Now this time you are going to apply the mechanical pressure, or you are going to compress the the actuator, or compress the configuration what you have developed, or the system. Let's say you have applied the mechanical pressure in the thickness direction. So because of this mechanical pressure application, the system is going to give you any kind of potential difference, and that potential difference you can utilize as a harvesting. You can harvest this type of generated potential difference to develop the electrical energy. So the same system now we have reversed, and we have achieved the generator configuration. So let's take very simple example. Let's do some very basic calculation to develop the energy harvester. Very simple type of energy harvester. So let's take let's say while we are running in our you can say that morning walk, let's say. So how much amount of energy we can generate from that, available form of mechanical, energy from the, you can say that we while walking or while running, we can utilize the available form of mechanical energy we can harvest in the form of electricity. So let's do a very simple calculation. So while running, or let's take a very common readings. Typically, the average weight of healthy human being is, let's say, 70 kg, and typically while running, so 70 kg. So while running, we are performing some kind of mechanical work. So available mechanical work is 70 kg into G. Let's say G. Let's take the value of G as 10. And suppose we are having, so 700 Newton force we are going to apply typically while running. Uh, and then this mechanical force has to be utilized to supply the as a mechanical pressure to the actuator, and let's say, sorry, to the generator. And let's say the generator configuration is attached to the shoe of the human. And this available means force while running, 700 Newton we have applied. So available form of means what is the amount of work we are performing while running. So typically while running, we are covering nearly 0.01 meter distance. So we are having the mechanical work, let's say 700 into 0.01 meter. So we are having the mechanical energy to harvest 7 joule nearby. So let's say in every means what is the availability of the mechanical power. So nearly, let's say, in every cycle and while running, you are having nearly, let's say, 1 hertz. So 7 watt of energy we can, mechanical power we can harvest. So let's say our system is not having good efficient. So let's say the available form, whatever we are having, 7 watts, but typically we can actually harvest, let's say, nearly 50% of available mechanical power we can harvest, or nearly 3.5. So that is actually matching the range, whatever the power is needed to charge your mobile phone. So you can design such type of generator with the help of this dielectric elastomer to while running in the morning, you can use the, you can charge your mobile phone. And similar kind of various different type of systems also developed, so to get the power from the same while running. And then this power, mechanical power, available form of mechanical power can be harvested to actually give you the power the different gadgets sometime people are utilizing. So similarly, you can also generate some amount of, you can harvest different type of, means there are some another example where you can harvest the available mechanical power in order to generate electricity. So again, this is the second example. Let's take simple toll point. So here various different type of vehicles are coming, and you have to design the toll road in the form of smart tiles. So with the help of this dielectric elastomer, so you can develop the dielectric elastomer based generator. So here, what is the amount of the mechanical pressure you are having while going the vehicle. So nearly the rough calculation are the follows like this. So nearly the vehicle weight is 2000 kg. So 20 kilonewton each vehicle is can give you the mechanical force. So mechanical work or mechanical energy, how much you are having. So 20 kilonewton per vehicle. And the each step, let's say this vehicle is going to cover the 0.1 meter step. So nearly it is having 2 kilojoule energy, mechanical energy is available to harvest. So let's take 500 vehicle per hour is typically in a city is going to move. So so how much amount of per hour, and you can calculate per day. So let's say 3 kilowatt hour per day amount of energy you are having, uh, which you can harvest whatever the, if you are using the efficient system. So at least whatever the amount of energy you are having, you can utilize or you can harvest such available form of energy to ignite the toll light, let's say. So what is the toll light requirement is nearly 0.1 kilowatt hour per day. So, and similarly, whatever the form of, energy you can harvest, means in the form of electrical energy you can harvest, and you can utilize in a very, uh, whatever the system you have attached in the, means whatever the system you can utilize to energy. So now, uh, typically, we have seen the introduction about the what soft actuators are, what dielectric elastomers, and how we can utilize the dielectric elastomer to develop the actuators and generators. So now let us discuss means fabrication of a basic soft actuator. So to do the fabrication part, of course, we have to list down what are the things we require. So typically, to develop the basic dielectric elastomer based actuator. So of course, first you need the BHB polymer, and of course, uh, you are making the soft actuator, but to not 100%, you can say that all the things are to be needed in the form of softness. You need some kind of a rigid frame as well to provide some kind of rigidity to the system. So acrylic typically acrylic material typically we use to make the frame. And of course, to put the carbon grease, I mean, to make the electrode, we require the carbon grease, which is coming in the form of simple, what you can say that tube. And of course, you need copper tape, a very thin metallic tape, and sometimes you can also replace this copper tape with aluminum tape as well. But compared to aluminum tape, you are having the, I mean, your copper tape is having very good performance. So that is going to utilize to connect the actuator electrode with the power supply, wires. So these are the very common, very important things you have to require before developing or before fabricating the soft actuators or soft dielectric elastomer based actuator. And of course, in addition to that one, you need some kind of additional, I mean, things like a scissor, cotton, so plastic, gloves. Of course, whenever you are going to perform, the fabrication of the actuator, so you have to deal with the carbon grease. So to avoid the things, you have to wear the gloves. And of course, voltage power supply is needed. And of course, as we have discussed that the voltage requirement, particularly for dielectric elastomer, is very high. So it is in the form of kilovolt. So you have to amplify the voltage. So high voltage amplifier is needed. To get the high voltage power supply. So this is the fabrication process. So of course, and typically whenever you are actually making the soft actuator, or typically this is the things you have to pre-stage the actuator. So pre-staging gives you the benefit in terms of the good performance. So there is a physical reason by which actually, if you can not, if you are not pre-staging the system, then you are actually not getting the good performance. So the pre-stretching plays a very important role to enhance the performance of the actuator. So in the frame, we are putting the membrane after pre-stretching, and then you are putting the carbon grease. So whatever the area you have covered by a carbon grease, that is actually we have that is the active zone or active area. And in that active area, means that active zone or active area, we would like to attach by a copper tape So, and this copper tape upper side and lower side can be connected with the power supply. And of course, after switching on the power supply, you are getting the actuation in the actuator. So the complete things, you can see that sometime this is the actuation track testing facility we have developed here at NIT Bhopal. So similar kind of activity we are going to perform. So the actuation, how the actuator is going to give you the actuation, we are going to see in a video. So just quickly let me show you similar kind of facility we have developed. And not only the actuator, so means dielectric elastomer based actuator people can develop. So people can also develop the soft gripper. So in order to make the soft gripper, you don't need the BHB polymer. So in order to develop the soft gripper, you may require liquid silicone. So just by utilizing the liquid silicon, you can develop a very small, means very simple type of actuator. So this is the some UG students have developed the 4-finger based soft gripper. And little bit more advanced, if you are getting the gripping in a very efficient sense, then you have to design the fingers in a very appropriate way. So to get the gripping, or to get the means a very gentle type of or kind of human kind or mimicking a human gripping, you have to apply the new nets in the new nets in the fingers. So here you can say the procedure, how the means some students, UG students at NIT Bhopal, they have developed the 3 fingers grippers. So initially they have actually make the design for the finger, and these how much the size of the new net we have to choose. They actually the size, I mean, that is going to play a very important role to get the good gripping. So after making the mold, and we have the liquid silicone, and means at the same time you are having the binder. So whenever you are going to purchase the liquid silicone, at the same time they will give you the binder also. So you have to mix them together in a very means in a equal in amount. So whatever the volume you are taking the liquid silicone, in the same volume you have to take the binder. So you have to mix it properly, and then you can simply pour the mixture to the designed mold, and you can have the you can have the finger. And later on, multiple finger you can fabricate, or you can later on you can design the this system where you are going to apply the compressed air to get the actuation, and you can design the system in such a way that you can control the actuation of the gripping actuation with the application of the electric with the application of the pressure control. So this is the kind of 3-finger soft gripper UG students have developed here at NIT Bhopal. And similar kind of gripper also we have proposed to DRDO, and we have got the funding from the same DRDO organization. So they were requiring the different type of things, like they have said that they need 3 or 4-finger based gripper, and they require minimum 4 degree of freedom, independent finger control, and they would like to means they were saying that they have to actually design, we have to design the gripper so that can actually take the weight up to 5 kg. So these are the few requirements I have listed down. So they need closing and opening time less than 1 second, and different type of grip modes. The gripper means they need different type of object library they would like to pick and place in a very smoother sense. So these are the few requirements they have given, and based on their requirement we have proposed the design. And of course the gripper application is very broad. So you can utilize the gripper in agriculture as well. So here you can see that there are there are harvesting some food or some kind of vegetables from the garden, so you can utilize the gripper. So similar kind of gripper things also, you can you can utilize the gripper in assistive technology as well. So this is the system at IIT Delhi people have developed. And similar kind of things, this is the this is not this is additional things with the help of the change in the viscosity. We can develop the small soft robot. So that is ongoing work at NIT Bhopal. And these are the few things not related. So now I would like to show some videos related to the actuator development. So then we can close our talk. So please have a look this video. Yeah, so we are getting the wrinkling in a particular threshold value of the applied electrical voltage. But if further increasing the voltage can break down the system. Yeah. So this video shows different type of dielectric elastomer based actuator. And second video I'm just going to run, that is going to give you the knowledge about the pneumatic based actuator. So here we are actually ignoring the electrical voltage control. So with the application of the pressure control itself, we can get the different, means we can get the actuation, and different type of actuator can be developed. So please have a look here. So how we can develop? So this is the liquid silicon based actuators development video is going to show you. Spider-like actuators you can also develop with the pressure control. And the material you have used, that is the liquid silicon. first you have to design the mold. And the designing of the mold plays a very important role to get the smoother actuation in the actuator. What will be the new net size? So you have to think about, and different new net size is also changing the actuator performance. Yeah, this is the liquid silicon, also known as EcoFlex. So it is coming as a liquid in the form of liquid form, and also parallelly you are having the binder. So you are mixing them together in the same ratio, 50-50 ratio. So to remove some kind of bacteria, you can also put some kind of chemical before pouring. So you are molding the liquid silicon mixture, and then you have to heat up, and sometime you may have some bubble. So this is the very challenging things to avoid. You have to deal with the bubbles. So you can heat. You can also put in sunlight as well, but that needs a long time. Sometimes you can also provide heat via this. If you want to include some color, you can add it. Yeah. So basically, with the help of the pressure control, you can get the actuation. So now I'm going to. So anyone, if you are having any kind of doubt, please, I'm going to invite you for any question.
Yeah, audience, any question? It's such a nice and wonderful talk. And I mean, this talk is special in the context is that professor has not used any mathematical, I mean, big mathematical equations. So he has guided us with a simple experiment through which we can make soft robots. And this is what is the very strong advantage of this talk. And we are extremely thankful to the professor for giving us the experimental ideas and exciting things that we can create in our lab. And we can, with these small items, we can create a hell lot of practical applications oriented robots and all this. Okay,
Thank
so
you, sir.
please ask any question. Thank you. So please ask any question, whatever you have. Please feel free.
Hello, sir.
Hello, sir.
Yes,
Yeah.
yes.
Good evening, sir.
Good
So,
evening.
nice talk. This is Balakrishna Reddy. I'm PhD scholar.
Yeah.
Sir, the same elastomer concept, can we apply like super capacitors?
Yeah, actually, the same concept, the similarity, what you are observing here in the capacitor, we also have the electrode kind of parallel plate capacitor. The concept is
Yes.
same, kind of, you are having the positive, charge density one side, negative charge density another
Yes.
side, and in between you are having some kind of, dielectric material. That's why the dielectric word
Yes.
came from the same concept.
Yeah.
So yeah, of course, the concept we have taken from the capacitor, means how the capacitance is to be developed in the system. So of course we can say that the same concept we have used here.
Nowadays, by using polymers, we are doing no, sir. Same concept, I think it is applicable by same elastomer concept. I can inculcate in a capacitor and I can develop a super capacitor.
Right.
Is that possible? My idea is this.
Super capacitor, I'm not getting which type, in what sense the super capacitor means you are talking about. Of course, this elastomer is also known as the, means we are using the capacitance concept to
Yes,
develop
yes,
the actuator.
yes.
So maybe I'm not getting your question. Uh,
No, no, no. You are right, sir. But same application, if we do, what are the consequences? Anything did you try? Because by looking at that,
okay.
your concept, I got some ideas regarding we can connect in the capacitors also to regenerative braking and all to store the charge much.
Okay, so maybe, but here storing of the charge we are not talking about. Maybe in the super capacitor it is possible, but here the concept is looks like same, like we are having the parallel plate configuration, and
Yes.
we are getting the reduction in the thickness direction. I mean, whatever the means in between we are having the dielectric material. Okay,
Yes.
so that dielectric material is going to shrink because you are having the attraction of means a kind of force in between the electrode.
Yes.
So
Yes.
parallel plate configuration we are having in this dielectric elastomer system.
Oh, oh. Thank you, sir.
Thank you.
Yeah, any other question, please?
Good evening, sir.
Good evening.
Yes, sir. I have one doubt that in lab I was conducting the experiment for getting the wrinkling pattern,
Right.
but my pet it was not clear, and after certain value of voltage it breaks down. So what should
Okay.
I make changes so that I get the clear wrinkling pattern?
Okay, so I think I can remember you. You have also performed in our NIT Bhopal lab also, I think, if you can remember. Yeah, right. So
Yes,
to
sir.
get the wrinkles, right? What means first thing, which type of voltage you are going to apply? See, to get the wrinkling, you have to apply a certain threshold. You have to reach the
Okay, sir.
certain threshold first. But which type of polymer you are going to utilize? Like means you are utilizing the BHP polymer.
Yes, yes, sir. BHB 4910.
BHB 4910. So in what amount of voltage you have reached? Means actuation you have
4 kV.
observed, and it means just
Yes, sir.
application of the.
Very minute, very little, and suddenly it breaks.
Okay, no. In between, so what you will see, you have to track, or you can track all the images in between. In a way, actually, that
Okay, sir.
time is very less. So you can
Yes, sir.
track complete, you can make one video, and then you can track the deformation in a very slower sense. So you will observe the, of course, actuation in that duration.
Yes, sir. One thing
Yeah.
I just saw in your video that the carbon grease the person was applying in by brush, and
Mhm.
I applied little thicker layer, I
That is
think.
also, that is the also important actually parameter, in what manner you have applied the, you have made the carbon grease. So even though if you are putting the carbon grease in a very, suppose you have the thickness of the carbon grease is also playing a very important role. So if you are changing the thickness of the carbon grease, that is also going to affect the, wrinkling observation and breakdown. And of course, even though the carbon grease application, if you are having in some, if you are making the pattern in some angle, that is also even going to affect your observation of the
Got
wrinkling.
it, sir. Got it.
So there are multiple things while performing the experiment you have to take care. So of course, but that is sure, in a certain threshold value, means after reaching the certain threshold value, you can observe the wrinkling. Maybe the time duration is very small to get the wrinkle, and up from wrinkle to the breakdown. But
Yes, sir.
you can make the video and then make the slower. You can use that image processing and then slow down the pictures, and then you will of course see the wrinkling state.
Okay, sir. Got it. Thank you, sir.
Okay. Okay. Thank you.
Okay, it's a very nice presentation. I'm having one question. Like,
Yes, sir.
can you explain to the audience that why this, as you talked about this project of DRDO, like
Yes.
what are the things that we cannot perform in the traditional robotics, what we can
Okay.
perform in this soft robotics field?
Okay, so basically in the DRDO projects, they were trying to, they were asking different type of, first thing, different type of, modes or gripping modes. First thing that can also be performed by conventional gripper, conventional means robotic gripper, but human-like gripping, that is very difficult to get from this conventional gripper.
Okay.
Yeah.
Yeah, good. So I think we got in this today's lecture, we got a various dimensions of this workshop. In the first, we got the mathematical things where the speaker talked about different mathematical form of it. In the second part, we got about the MEMS. And in the third part, we got the knowledge about the magnetoactive material, their stability, and their different constitutive relationship, the fundamentals. And in the fourth, we got the entire thing is dedicated to the experiment. So it completes today's discussion towards the main theme of this workshop. And I must thank all the speaker as well as Professor Deepak Kumar for giving such
Thanks.
a valuable insight of this field, and at the same time giving us the exciting talk of which are of practical. It's not lying in the pen and paper or in computer. It's lying in our day-to-day life, and means if we want, we can make it. So I'll thank Professor once again for his valuable time and wonderful talk. Thank you.
Thank you,
And
sir.
I
Thank you.
thank all the speaker. And today we conclude our this session. And tomorrow we are going to meet sharp at 10. Okay then. Thank you all.
Thank you, sir. Thank you, sir.
Thank
Thank you
you.
all.
Thank you.
Thank you.
Thank
Bye.
you. Thank you.
Thank you.